Thanks for the introduction, and thanks for allowing me to speak here. So today I'm going to talk about fast permutation property testing. This is a joint work with Jacob Fox at Stanford. So let P be a property, which you can consider as a collection of objects satisfying this property. We want to be able to distinguish quickly between the object satisfying this property or it is far away from this property. And if the object is in between, then we don't really care about the output. So some examples can be, does a graph contain odd cycles? Or is a function a linear function? Or does there a permutation contain no increasing subsequence of length 10? So you can consider for now permutation, for example, is the rankings of a bunch of websites. So traditionally in theoretical computer science, with the input size n, polynomial running time function algorithm is considered fast. But in property testing, so for example, if your input is a graph or the rankings of many websites, the input size is enormous. So even a quadratic tester is going to be slow. So we want to be able to make a decision by curing a very small portion of the input. So an algorithm does that. It's called a property tester. And this is going to be a randomized algorithm, and it's used to test the membership of a collection. So in the talk, when I say something satisfies this property, it's equivalent to say the object is in this property. A tester is called one-sided for some property P is such that it's able to make very good decision in two cases. So the first case is when this object has this property, then we want the tester to output the object that has this property. And the other extreme case is when the object is epsilon far from satisfying this property under some metrics, then we want with decent probability, we can output the object is not in this property. So here the probability 2/3 is somehow artificial. We can change that number to anything greater than a half by repeating this process multiple times. So another tester we usually consider is called two-sided. So this is the tester such that in both cases it will output with probability at least 2/3. So the two-sided tester is weaker than a one-sided tester because in the first case, when the object has this property, we also allow it to have mistake. And the goal is we want to know whether there exists a tester with constant Curie complexity. So here the constant means it shouldn't depend on the input size, and it can only depend on epsilon and the property. We further even want the constant Curie complexity to be small in 1/epsilon. So some polynomial in 1/epsilon will be great. A very beautiful and nice result in this, a general result in this field is done by Alan and Shapira in 2006. So they showed for any hereditary graph property P, which is a general property for graphs, there exists a one-sided tester. So you only allow mistake in when the graph is far away from this property. And so this property, and they show this tester has constant Curie complexity. And the metric they use is the edit distance, which is a very natural metric for graphs. So the edit distance is the fraction of edges you have to change, add or delete in order to change from one graph to the other. And a hereditary graph property is such that if a large graph is in this property, then any of its induced subgraph also has this property. Their tester is a very natural tester. So you pick uniformly at random m vertices from this graph, and you consider the induced subgraph on these vertices. And if this induced subgraph has this property, then you output the graph has this property. And if this induced graph doesn't have this property, then the tester should output it doesn't have this property. So it's also easy to see that from this tester, when the large graph, the original input has this property, because the property is hereditary, then the induced subgraph is also has this property. So this tester is at least one-sided. And by the definition of the tester, when the graph is epsilon far away from this property under the edit distance, then with high probability, or with decent probability, these induced subgraphs should not be in this property. So we can also translate into the corollary here. So when the graph is epsilon far from this property, then at least 2/3 of the induced subgraph will not have this property. Their proof gives an upper bound on the Curie complexity, which is at least Walser type in 1 over epsilon. So if you consider tower function as 2 to the 2 to the 2 with the layers of 2s is n, a Walser type bound is going to be iterating the tower function n times. And this bound is later improved by Collin and Fox to tower type for typical properties. So in fact, weak or no bound is a common drawback for tests for general property testings in this area, because usually regularity method is used, which will lead to a very large bound, or compactness argument is used, in which case no explicit bound is given. So the major open question for testing general properties for testing general property is that whether we can find a better Curie complexity in 1 over epsilon. And many long-standing problems in number theory and combinatorics are related to getting better bound for property testing. And we studied this we study this question for testing hereditary permutation properties, which is a general property for permutations, which I will define later. And in general, we show there exist testers with constant Curie complexity, not depending on the length of the permutation. It only depends on the property, and the constant Curie complexity is polynomial in 1 over epsilon. So before I go into the literature review and the formal statement of the theorems, let me first define what is a permutation and subpermutations, because this is going to be useful for the later talk. So throughout this talk, it's useful to consider permutations as represented in unit squares. If a permutation has length n, we usually consider is cutting the unit square into incongruent columns and rows, such that each column and each row has exactly 1 dot. And we read the permutation from left to right. So for example, the left graph shows the representation of permutation 42653 So you just read the value of the dot from left to right. A subpermutation is such that from the original permutation, you pick a subset of the dots and only consider the relative orders of those dots. And this gives us a subpermutation. So for example, if you choose the 3 red dots over here, then their relative order is 1, 3, 2. And so we say 1, 3, 2 is a subpermutation of the permutation on the left. A hereditary permutation property is similar to hereditary graph property. So it says if a big permutation is in this property, then all the subpermutation should also be in this property. So for example, P being the set of permutation avoiding 1, 3, 2 is going to be hereditary, because if the large permutation is avoiding 1, 3, 2 as a subpermutation, then any of the subpermutation of the big permutation should also avoid the pattern 1, 3, 2. And this is a graph this is a permutation here. So this is a permutation that is not in this property because it has a subpermutation of the pattern 1, 3, 2. And a very simple observation is for any proper property P, because it's proper, so it must at least avoid some permutation as subpermutation. And if the property P avoids sigma as a subpermutation, then if we know permutation pi contains sigma as a pattern, then pi should not be in this property. So that's how. So that's why in later it's very useful to consider a pattern avoidance for permutations. Okay, so since we need to do randomized testers, so it's also useful so we should define what metrics we're using in order to say a permutation is epsilon far from the property. So unlike graphs where there's the natural distance, for permutations, there are several different metrics that arise commonly in statistics and rankings. And we study the property testing with respect to those metrics. So the first one I'm going to introduce is called the rectangular distance. It's also called a cut distance. So ignore the formula for now. I'm going to explain this by the picture. So you remember we can represent permutations as a bunch of dots in unit squares. So here we have two permutations, the red one and the blue one. You draw a rectangle, a geometric rectangle in this unit square, and you cut. So for example, in this one, there are 4 blue dots and 2 red dots in this rectangle. So the discrepancy is 2. So the rectangular distance is defined as the largest discrepancy among all the rectangles you can have in this rectangle. And recall that the largest discrepancy at most n, because there are only n points, so we can normalize it by 1 over n in this formula, so that the distance is between 0 and 1. And this rectangular distance is analog to the graph cut distance, which is commonly used in weak regularity lemma graph approximation algorithms, and is also useful for counting subgraphs. And similarly, it also holds for permutations. So if 2 permutations are distance small in cut distance, then almost all the countings, the countings for subpermutations in these 2 permutations are about the same. So another commonly used metric is called the Earth mover's distance. So the name kind of suggests what this metric means. Again, we have 2 permutations, the red one and the blue one. The Earth mover's distance is the minimum distance I have to move in order to make the blue permutation go to the red permutation. What does that mean is you find a matching between the 2 permutations, and we have to move the blue dots along those bars of the matching to go to the red dots. And the Earth mover's distance is defined before normalizing the minimum distance I have to move among the optimal matching. So the mathematical formula is like this. So theta is going to be a bijection between the 2 permutations, which gives the matching. And so I minus theta I is going to be the horizontal distance each dot is moving along the bars. And this term is going to be the vertical distance each dot has to move along the bars. And we're minimizing all the matching theta. And the normalization factor here is 1 over n choose 2, so that the distance is between 0 and 1. A thirdly commonly used metric is called the Cantor's tail distance. It is commonly used in rankings. So this is defined as the normalized minimum number of adjacent transpositions, which means you are allowed to swapping elements into adjacent columns. So the minimum such adjacent transpositions you need to do in order to turn the first permutation into second permutation. So the number of adjacent transpositions you have to do to turn one permutation into identity permutation is going to be the number of inversions in that permutation. So I introduced 3 metrics, the rectangular one, the Earth mover's distance, and the Cantor's tail distance. And their relations is as follows. So the rectangular distance is equivalent to Earth mover's distance up to polynomial change. And both of these metrics are weaker than Cantor's tail distance, in the sense that if Cantor's tail distance is small, then the first 2 distances are small. So we can also sort of see it by their definition. So both rectangular distance and Earth mover's distance, you can sort of move the points both horizontally and vertically. But for Cantor's tail distance, it's less geometric because you are not allowed really to move the points horizontally. You're only allowed to swapping the columns. And another way to see it is you, given 2 random permutations of length n, then the Earth mover's distance is almost with high probability, the Earth mover's distance between the 2 random permutations is lambda 1, while the Cantor's tail distance is theta 1. So Cantor's tail distance is the strongest. So what does it mean after we translate into tester? So if I can give you a tester with respect to the Cantor's tail distance, then this tester is naturally going to be a tester for the weaker metrics. This is because if my permutation is far away under the even weaker metrics, then the distance between the permutation and the property is even going to be larger under the stronger metric Cantor's tail distance. But usually if we are testing with respect to the weaker metric, we can get a better Curie complexity bound. So now here I'm going to do some literature review for testing permutations. So one of the first nice results in this area is done by Koppen, Hayakawa, Moria, and Sampiero in 2012. So they proved that there exists a one-sided tester with respect to the rectangular distance. And they are using compactness argument, so it won't yield any explicit bound. But I have to say, so for their paper, they are using the very natural tester as well. So pick a random subpermutation and see whether that subpermutation has this property or not. And they further conjectured whether, they further conjectured that with respect to the candle's tau distance, this natural tester will give a one-sided, is going to be a one-sided tester. And this is confirmed in 2014 by Klimishowa and Krall. They proved that with respect to the stronger metric, the candle's tau distance, the natural tester picking a random subpermutation to see whether it is property or not is going to be a one-sided tester with Curie complexity. But their bound is a bit weak. So for testing even when for testing even sigma avoidance, their bound will be Ackermann type in 1 over epsilon. And we improved the bound with respect to the candle's tau distance, and it gives the Curie complexity to be polynomial in 1 over epsilon for testing sigma avoidance, and by using the same natural tester. And we come up with some other tester, and which will give better bound with respect to the rectangular distance, and is almost quadratic in 1 over epsilon with respect to rectangular distance. But I have to say, like, this bound is, so this tester is going to be two-sided. If we allow it to be one-sided, then the bound is going to be worse. But for typical properties, it's still going to be polynomial. Okay, so here is the formal statement of the main theorem. So given P to be any property that forbids sigma as subpermutation, then there exists a one-sided tester with Curie complexity polynomial in 1 over epsilon with respect to the candle's tau distance. The tester we use is the same as the tester as the previous work. It's a natural tester. So you uniformly at random sample a subpermutation of size m from pi. So what does it mean is if pi has length n, so you choose uniformly at random an m subset from 1 to n, and you look at the induced subpermutation on that set. And for this subpermutation, so if this subpermutation is in the property, we output it is in this property. And if it's not in this property, then we output the original permutation is not in this property. So again, it is easy to see that when the original permutation is in this property by hereditary, then the subpermutation is going to be in this property. And when the permutation is not in this, is far from this property, then with decent probability, the sample subpermutation is not going to be in this property. So the corollary becomes at least 1 minus epsilon fraction of the subpermutation of that size will contain a copy of the pattern that I'm trying to avoid. And this bound is the same as the Curie complexity in the theorem is going to be polynomial in 1 over epsilon, and the exponent or the degree of this polynomial is double exponential. So this degree, the double exponential comes from the Markov-Stadler theorem, and we also, so for this proof, we use both the Markov-Stadler theorem and cake fair cutting lemmas and some other combinatorics results. So this proof is quite involved, and I'm not going to touch the proof of this main theorem. So for this talk, I'm going to give some proof sketch for a much simpler theorem, which is testing with respect to the weaker matrix, the Earth mover's distance. So recall Earth mover's distance is you find a matching between the two permutations and see how far you have to move from the blue permutation to the red permutation. And the theorem we're going to give some proof idea for in this talk is given in this statement. So let P be any hereditary property, and we can show there exists a two-sided tester with respect to the Earth mover's distance, and the Curie complexity is almost quadratic up to log factor. And surprisingly, this Curie complexity is independent from the property. And also, our theorem is only useful when testing sufficiently large permutations.
Do these things apply to a relaxation of permutations, such as W stochastic matrices?
I think so, yes. Yeah. Yeah, thanks for the question. Okay, so this bound is now the optimal we can get. We can also improve the bound, so by removing the log factor. So we can remove the log factor by doing some more careful analysis of the proof. And we can further improve this bound to almost linear, epsilon to the -1 log square epsilon over 2. But this bound is going to be depending on P. So to improve from the quadratic bound to the almost linear bound, we have to use the Markov-Stadler theorem again. Okay, so before formally describing the tester, because we're not using the natural tester for this proof, have to define something called a blow-up of a permutation. So I guess many audience have already familiar with the blow-up for graphs. So for permutation, it's something similar. We're given a small permutation, say alpha equals 2, 4, 3, 1, which is the red permutation over here. The blow-up is such that each point blows up into a cluster of points, such that all those clusters form the shape of 2, 4, 3, 1. So the four rectangles here form the shape 2, 4, 3, 1. And those rectangles are disjoint horizontally and vertically. We don't really care about relative orders of the points within each block. So the main idea is the small permutation blows up into some rectangles, some collection of rectangles which form the same shape. And this is also called a block decompositions, where the blocks form the shape of the original small permutation. And a K blow up is such that each block contains exactly K points. So it's kind of an equal blowing up. Okay, so here is our tester. So it says given the original permutation, we sample a subpermutation of length m from it uniformly at random. We output the original permutation satisfies this property if and only if for any integer k, there exists one k blow up of the sample subpermutation that satisfies this property. So for OK, no matter how large the blow up we are required, you can find a blow up that is in this property. So k blow up again is each block contains exactly k points. Well, this tester for now sounds very scary because we have to check for any single k. But in fact, this is a finite check. It suffices to check up to some certain k. The reason is simple, but it probably still requires some thinking. So we can show for any length s, the largest k we need to check is some blow-up parameter kps, depending on the property. And this parameter, the blow-up constant, is such that for any permutation of length s, if there is a kps blow-up of this permutation in this property, then for any larger k, there is going to be a k blow-up of the subpermutation in this property. In other words, so kps can be considered as the size of, so the maximum over all permutations of length s and the minimum counter examples such that the blow-up is not in this property. So if you buy the fact that such a blow-up constant exists, then the tester above is going to translate into this tester, which sounds a lot more friendly. It says given a permutation of length n and sample pi prime of length m from pi uniform at random, then we can output pi is in this property if and only if there exists a kpm blow-up of the sample subpermutation in this property. And we'll buy the fact that this is a finite check because you are only checking for a certain size of blowing up. And the worst thing you can do is, or the most trivial thing to do is to check any single blowing up of this size. So usually it's hard to determine the blowing up constant exactly. But there are some facts about these constants which give us some decent upper bound. Okay, so first, So if translate the theorem into the corollary, and similar as before, given a corollary in the structure of the permutations, it says if a permutation is epsilon far from the property under the Earth mover's distance, then at least 1 minus epsilon fraction of the subpermutations of size m are such that all their Kp and blow up are not going to be in this property. Okay, so some examples of permutations and their blowing ups in or not in the property. So for example, we consider P as the set of all permutations avoiding the pattern 1, 2, 3 as a subpermutation. And assuming our sample permutation is just 1, 2, the very simple one, like this one. So we want to show for any K there's a blow up of this permutation that is not in this property, which means the blowing up is not going to contain the pattern 1, 2, 3. So the easy thing we can do is in the two blocks, which the two blocks form the shape of 1, 2, we fill in monotone decreasing for the subpermutations. And it's easy to see that this permutation is not going to contain the pattern 1, 2, 3 because I cannot find an increasing sequence of length 3 in this blowing up. So this is a very simple and intuitive example. But for some permutations and other properties, the bound is going to be slightly trickier. So for example, if P is going to be the set of permutations avoiding two patterns, 1, 5, 2, 4, 2, 3, 4, and 1, 5, 4, 3, 2, is a simple exercise to see if your sample permutation is 1, 3, 2, then for any K less or equal than 4, you can find a K blow up of pi prime that avoids both of the two patterns. But if I tell you K equals to 5, then all the 5 blow-ups of the subpermutation is going to contain at least one of these two patterns by Ardouch-Zaghari's theorem. Okay, so I promise you that there's some simple bound for the blow-up parameters. So for typical property P such that the property P is the set of permutations only avoiding a finite number of permutations as subpermutations, then this constant is going to be, then this blow-up constant Kp is going to be bounded by a constant, which only depending on the length of the minimum permutations you are avoiding. So this is not a very easy fact. So basically it says if we only allow monotone, it says like if we only allow monotone increasing or decreasing fillings in each blocks in the blow up, then as long as the block size is at least the largest length of the permutations you are avoiding, then if a permutation, then if any K permutation is not in this property, then the side length of sigma, the length of the sigma is going to be enough. And by Ardouch-Zaghari theorem, you know if I have a sequence, if a permutations of length K minus 1 squared plus 1, then there must exist an increasing or decreasing sequence of length K. So that's how this bound comes from. So this is a nice one. So if we are lazy of checking exactly what is Kpm, then we can simply use this bound. And this bound has nothing to do with the length of the original permutation n. But for some other properties, the bound is even better. So for PB, the all permutations avoiding a set of twin-free permutations as subpermutations, then the blow-up constant is exactly 1. So a twin-free permutation means there are not 2 points in the permutation that are in adjacent columns and rows. So the relative order of these 2 points to all the rest points are the same. So that's why they are called twins. So if Kpu equals to 1, then tester basically says if there exists a K blow-up of the subpermutation in P for any K, this is equivalent to say the subpermutation itself is in this property. Which means in the very nice case when Kp equals to 1, we don't have to check a blow-up of the sample subpermutation. It becomes a natural tester that we just need to see whether the subpermutation itself, the sample itself is in P or not. So the corollary becomes, assuming we are given the property that it avoids a set of twin-free permutations of subpermutations, which happens very often, then if pi is epsilon far away from P, then at least 1 minus epsilon fraction of the subpermutations of size m is not going to be in this property. So in this yeah.
The property of being twin-free is not hereditary, right? Is it,
So it's avoiding a set of twin-free permutations. So it avoids a set of subpermutations, and those subpermutations are twin-free. Yeah. Yeah, it's a bit hard to.
sorry.
Okay, thanks. Okay, so now I'm going to give some proof idea of the main theorem. So remember, our task is to say if pi is in this property or is epsilon far away with respect to the Earth mover's distance, then our randomized tester should make pretty good decision about whether the original permutation is in this property or not. And our tester is we output pi is in P if and only if, there's a typo. Okay, if and only if for any k there is a k blow up of the sample in this property, which is equivalent to say if and only if there is a kpm blow up of the sample pi prime in this property. So we need to check two cases. So the first case, which is relatively easier case, is when the permutations in this property. So when these permutations in this property, we want our tester to output with decent probability that the pi is in this property. So a key observation for this part of the proof is that when the original permutation is large enough, then pi typically contains a large blow up of the sample subpermutation. So this observation has nothing to do with pi in this property or not. So this is a general observation holds for any large permutations and its subpermutations. So if we buy this fact, so if we agree on this observation, then what does it mean? It means if my original permutation is in this property, then since the property is hereditary, then this large blow up of the sample is going to be in this property. And our tester will output pi is in this property because this large blow up of the sample is in this property by the description of the tester. So I'm going to give some intuition why this observation is true. So we represent the huge permutation in unit square, and the dots, including the black ones and the red ones, are all parts of the permutation. And the red triangles are going to be the sample points. So if we look at this representation globally, then we can see there are some relatively dense regions and some relatively sparse regions. And it is very likely when the original permutation is large, so all the sample points come from the dense regions, and no sample points come from the sparse regions. And so in this case, so for example, we have 4 dense regions, the green rectangles over here, and all the sample points come from the dense regions. And for each of the sample, because it lies in some very dense regions, so there are lots of other points in the original permutation that are around these sample points. So you can sort of imagine growing some neighborhood from each of the sample points. And each of the sample points grow into some small neighborhoods. And those small neighborhoods are disjoint horizontally and vertically. And so they form the shape of the samples, the subpermutation from the sample. And that blow up is going to be in the original permutation. So that provides some intuition about why, when the original permutation is large, it typically contains a large blow up of the sample subpermutation. So the slightly harder, so the harder case is in the second case. So we want to show when the Earth mover's distance between the permutation and property is large with respect to the Earth mover's distance, then typically our tester will output the permutation is not in this property. So again, our tester is, so uniform and random sample with subpermutation from this property, from this permutation, and you output the permutations in this property if and only if for any k there exists a k blow up of this sample subpermutation in this property. A key lemma says typically we can construct a blow up of the sample permutation that is close to the original permutation under Earth mover's distance. Again, this key lemma has nothing to do with pi in this property or not. So this is also a general lemma that holds for all permutations and their typical samples. So when I say typical, I mean with high probability, the thing will happen. And if we agree on this fact, then we can prove by contradiction to show why our tester works well in the case that pi is far away from this property. So suppose the tester make a mistake and it outputs pi is in this property, then from the description of the tester, it will output pi is in this property if and only if all the there always exists large blowups of the sample permutation that is in P. And I kind of just use the fact that all the blowups of the sample permutation are close to each other. Then this means this large blowup we construct from the key lemma is going to be close to the property P. But then because this blowup we construct is also close to the original permutation, it means the original permutation pi itself is going to be close to the permutation. And this gives us a contradiction because in this case, we already assume the distance between pi and the property is very large. So the main thing for this case is to see how to construct a blowup of the sample permutation, the red small permutation, that is close to the original permutation pi. So look at this picture. So how can we move the black points such that such that the new permutation looks like the blowup of the sample permutation? So there's also some very intuitive way of doing this. So if we want to move the original permutation to mimic a blowup of the sample, the first thing comes to mind is we just move all the points in the permutation to the closest sample point. It is 2. So here the dashed lines indicates which sample point is closest to that point in this permutation. And then you just move all those points to those sample points. So now I have 4 clusters of points. And those clusters basically look like the shape of the original sample subpermutation. And this sort of already becomes a blowing up, because I have 4 clusters of points which form the shape of the sample permutation. But we are not done yet, because we need to obtain a permutation. And for permutation, we need each column and each row, each congruent column and row has exactly 1 point. But here I kind of squeeze everything into 1 point for each of the cluster. But it doesn't really matter too much. So we can sort of move each cluster a little bit and then move the points within each cluster a little bit so that this guy becomes a permutation. And this is a blowing up. And so this is going to be the blowup we construct. And the goal is to show the original permutation on the leftmost picture is close in distance to the final permutation we construct. There are in both of the steps, we have moved the permutations a bit. So the first one is in step 1, when we move all the points to the closest sample point. And the second step, when we kind of move locally those points in order to obtain a permutation. But the good news is the total distance I moved in the second step is not very large compared to the distance I moved in the first step. So in fact, the total distance I moved in the second step is within constant factor of the total distance I moved in the first step. So by triangle inequality, we just need to bound the total distance I moved in the first step in order to show the distance between the original permutation and the final blowup I construct is going to be small. So I want to bound the total distance I move in the first step, which is what was the distance I moved so that each point goes to the closest sample point. And this is done by dyadic partition, which is a commonly used technique in computer science, theoretical computer science. So a dyadic partition works as follows. We say a square is dense if it contains at least quadratic in epsilon number of points of the original permutation. So here our definition of dense is slightly unusual because our definition of dense has nothing to do with the area of the rectangle. So we only count the absolute number of points in that rectangle. And the original unit square is going to be dense because it has n points since it contains all the points in the permutation. So the original unit square is going to be dense. So the dense square splits into 4 squares. So each time I have a dense square, it splits into 4 congruent squares. And for the congruent squares, for smaller squares, we again count the number of points of the original permutation in those squares. And there are 2 things can happen. So the one case is the small square becomes dense, or the small square becomes sparse. So if the small square is sparse, then it stays sparse. It doesn't move anymore, so it becomes freezed. But if the square is dense, it continues splitting. So we continue splitting all the dense squares into congruent subsquares, and the whole procedure stops if all the squares become sparse, in which case I cannot do any movement anymore, or when the smallest square is of side length linear in epsilon, so some small constant times epsilon. So if we imagine the whole dyadic procedure, we can see towards the very end, the unit square got the partition into sparse squares of different sizes and some small dense squares. And all those dense squares have side length exactly epsilon over 16. So it kind of becomes a picture look like this. So we want to bound the total, so again, we want to bound the total distance. Before that, so recall a dense square contains at least epsilon squared times n over 4 points of the original permutation. So by a union bound, the probability that some dense square contains no sample point, which is the event we don't want it to happen, is going to be, by the union bound, the total number of dense squares multiplied by the probability that the specific dense square doesn't contain any sample point. And since a dense square contains at least epsilon squared n points of the permutation, the probability that none of the sample points hits this dense square is going to be 1 minus the number of points in this permutation, in the square, and to the power of the sample, because all the samples are chosen independently. And if we work this math out, you can see this is bounded by epsilon by our choice of m, the Curie complexity. And therefore, we just show that the probability that some dense square contains no sample point is bounded above by epsilon. So we can condition on this event and assume all the squares, once dense, will contain some sample point. And now we are ready to bound the total distance we move, which is the total distance each point in the original permutation moved to its closest sample point. So there are 2 cases, again, we need to consider. So the first case is we count the total distance the points in the dense square moved. So in this example, because we are already under the condition that all the dense squares contain some sample point. So if a point is already in a dense square, then we know the closest sample point it moves to is bounded above by the distance. This is to the sample point in that dense square itself. And we already know the dense squares are very small in the side length, which is epsilon over 16, then the total L1 distance, though the points in the dense squares move, is at most twice the side length of the smallest dense square. And so the distance it moves is small. And we can be lazy and bound the maximum number of such points, which is at most n, because I only have n points in this permutation. The second case is we have to consider the points from sparse squares of side length 2 to the minus I. And how much, what's the distance such a point will move? So remember, we are under the condition that each square, once dense, will contain some sample point. So if this square is sparse, it means it must come from splitting of a dense square, which is this square. So in the previous step, this square is dense, and then therefore it can split into 4 squares, and then this square becomes sparse. And then we are under the condition that this square contains some sample point, say, for example, here. So the total distance, this point moves at most twice the side length of this square, which is 2 times 2 to the minus I minus 1. So the distance each point moves is not too small, but the number of such points is small because this is a point in a sparse square which doesn't contain too many points. And the number of such points is at most 2 to the 2i, which is the number of sparse squares of side lengths 2 to the minus I, the upper bound on that. And each of such squares contain at most this many points because the square is sparse. So the total distance we move is by adding up all these two cases together. So it's some geometric series, and after you do this, you can see the computation comes out easily. The total distance we move is at most epsilon n over 4. So it kind of proves some proof idea to show that the original permutation is close to a blow up of the sample permutation. So the conclusion is for testing hereditary permutation property, we have some testers. One with respect to the Kendall-Tail distance, the Curie complexity is polynomial in 1 over epsilon, with the degree is sort of the constant coming out from Markov-Stadler theorem. And this is for testing P being sigma avoiding. And the polynomial bound can be generalized for testing some other typical properties. And with respect to the weaker metrics, which is the Earth mover's distance and the rectangular distance, we are able to obtain polynomial bound for two-sided testers with the degrees is very small, 1 or 2 or 4. And even there exists universal bounds, not depending on the properties. And for one-sided testers, the Curie complexity is slightly worse, because that will depend on the blow-up parameter I just described in this talk. Okay, so there are some open questions. So the first question we're very interested in is, for the Earth mover system, so for the two bounds depending on the property, can we actually remove the log factor? And the second open question is, can we prove some quadratic bound for testing with respect to the rectangular distance? So here we obtain this bound is because the Earth mover distance is equivalent to rectangular distance. It's because Earth mover distance is easier to work with. For testing with respect to the Earth's rectangular distance, we first translate to testing with respect to Earth mover's distance. And by the equivalence of the two metrics, we obtain the bound for the rectangular distance. So the open question becomes, can we work directly with the rectangular distance and now obtain a better bound? And another question is quadratic bound actually a lower bound for testing with respect to the rectangular distance? And can we use similar methods to approximate the rectangular distance between two permutations up to some additive errors? Yeah, that's all for my talk today. Thank you.
Questions?
Yeah.
And is this parameter k of p for hereditary properties always computable, or do you have examples where it's not?
So we have some upper bound for it. I don't know whether there's a very efficient way of checking it.
So it can be computed for any property?
No.
Speak up, Matthias, please.
So my question was whether it's decidable to calculate, or is it computable to calculate this parameter k of p with George?
I guess not.
Probably not. For simple ones, it typically is, yeah. So if it's a finite set of avoiding, then you can determine it. But I would expect like
in the graph
in the graph case, I would expect it to be like that in general.
So your method is so general, so maybe it can be used to prove similar results, at least for similar distance, for higher dimensional permutation, like a Latin square, because it seems that everything here should work, unless there is some sort of divergence of series in this Dyadic something. So have you tried it?
I haven't. But that sounds like a very interesting direction. Yeah, thank you for putting it out.
Any other questions?